Good afternoon, everybody. I would like to thank the organizers for inviting me here. It's a pleasure. So I'm going to present that we have been doing on modeling and design of photonic structures for quantum trapping. And this work has been done in collaboration with Victoria Esteso, also here in the audience and currently at Lens, and with Professor Miguel at the Institute of Material Science of Seville, also in Spain. And this is where this work started, and I would like to highlight this fact that this work was done in the framework of a multifunctional optical materials group. So as we have seen during the previous talks, the Casimir force establishes that two plates perfectly conducting, infinitely thin at zero temperature and in vacuum will be attracted by a force per unit area given by this expression here, where D is the distance between the two plates, and because of this distance dependence, it is important to measure this force in the nano and the micro scale. One easy way to understand this attraction between the plates could be paying attention to the difference in the radiation pressure felt by the two plates, considering the amount of modes that fit outside the cavity they form and inside the cavity it formed. And because of this difference in the radiation pressure, these two films stick together. A few years later, Lifshitz and collaborators made an extension to real materials in the sense that the optical properties or the permittivity of the materials was taken into account, and made the extension to finite temperature and to other different geometries like the sphere and the plane, or a multi-layer structure and a plane. And since then, there's been a huge amount of work trying to, for instance, as Bettina said, including more complex geometry. And one of the most interesting results of this extension is the prediction of a repulsive force under certain conditions. And this is interesting also, as Bettina said before, because it has important technological applications in the so-called nano and micro electromechanical devices or systems, because at the end of the day, this attractive force is the cause of the malfunctioning of these devices when some of their component parts stick together. But it has also inspired biomaterials, and it has also other nanotechnological applications, including microfluidics and drug delivery. So in order to give a context on the difficulties in measuring this force experimentally, here I show very briefly and just highlighting some works, but there are tons of them, where we can see how things develop trying to test this force experimentally. So we have the Casimir effect and the Lifshitz extension, these two predictions, and then during the next decades, there were some experimental attempts trying to measure these attractive forces, but as we had said before, we need to measure this at the nanoscale, and the techniques at that time were not enough. So then, near the first, the most accurate measurement of attractive forces is considered to be the experiment by Lamoureux, where we have a sphere and a plane, and these are attractive forces. And then there were some more measurements, and what is considered really the most accurate measurement for attractive forces by Deca and collaborators. So we started here. We are in 2005, and we have just measured attractive forces between a sphere and a plane. Then in 2009, the group of Capasso also measured for the first time a repulsive Casimir force in 2009, again between a sphere and a plane, and also considering a fluid in between the sphere and the plane. The part of the difficulties have to do, as Karsten also said before, because of the presence of the other forces, like the double layer force, the rugosity of the samples, or the presence of patch potentials. And then, in the last years, there's been a novel approach for measuring the repulsive force in the plane-plane geometry. And this is additionally, it has an additional interest, which is that between plates, this force is more intense than between a sphere and a plate. So I'm talking about this approach in which we are going to have a quantum trapping of a plate, which is forming an optical resonator. All these approaches, which are both theoretical approaches and experimental evidences of the same, consider that you have a metal film that is quantum trapped under the action of a repulsive Casimir force in a fluid, and then you have a substrate, which is also a metal, and then you are forming an optical resonator and in which one of the mirrors is levitating. And this is a milestone in the timeline that I showed you before, because this is the first time that the repulsive Casimir force in between two plates is being measured. So in contrast to previous approaches with the sphere and the plane geometry, where we have a cantilever and we can measure also this repulsive force, with this novel approach, we are going to observe this quantum effect from far field measurements. It is a very nice idea. So how can we have this quantum trapping? So basically what we need is that the total force acting on our film is going to be balanced, right? So we can have a scheme like this where we have an attractive force between the two plates at short separation distances that changes to be repulsive at large separation distances that is balanced by buoyancy and gravity, for instance. Or we can have another scheme, which is this one, where we have repulsive Casimir force at short separation distances, which changes to be attractive at longer ones. And again, this is balanced by buoyancy and gravity. The difference between the two schemes is that in this case, we are going to have an unstable equilibrium position, meaning that any deviation from that position will make our film float or sink, whereas in this other, here. In this other scheme, the position is going to be stable, meaning that under deviations, the film will return to that position because we have forces pointing in that direction. So how can we get repulsive Casimir forces? Well, for the plane parallel geometry, it has been established that the dielectric function of the interacting materials need to fulfill this inequation in comparison to that of the mediating fluid in a broad spectral range. But note that this inequation, well, this condition is a necessary condition but not sufficient, and then that it is evaluated at the so-called Matsubara frequencies as we have seen before. By doing so, we are rotating from to the complex plane, and we are integrating the losses of our materials in an infinite frequency range. When we do that, rapid oscillations occurring in the integrand when computing the force are therefore eliminated, as we have seen before. So what does it mean? No, I come from a multifunctional optical materials group. We try to modify the optical properties of our materials. And the thing is that here I'm showing you the absorption coefficient of a bulk silica material, which is related to the losses like this. This is the real part of the refractive index. And then when we do the rotation, anytime we have an absorption band, we get a slope in our curve. And whenever the system is transparent, we have planar bands. So in the end, we need to have a look at plots like these ones where we are characterizing our materials, trying to find that inequation that I told you before. So once we have that, it is possible to compute the Casimir Lifshitz force per unit area in any multi-layer scheme given by this expression here, where we have the multiple Fresnel coefficients of the bottom and the top interfaces of the fluid mediating the interaction, which in turn depend on the simple Fresnel coefficients along all the slabs, which depend in addition to on the dielectric permittivities of our material. So this is the way that the force is mediated by or depends on the optical properties of our materials evaluated at the Matsubara frequencies. So with this figure here, I would like to show you the kind of systems we can fabricate in the group. And basically, I can sort them out into optical resonators, composite materials, or multi-layer structures. And with this, we do several things like designing efficient, flexible, and colorful solar cells, for instance. So I'm going to focus here on these two groups, and then Victoria in the audience will tell you some results on multi-layer structures. So as I said before, in terms of the optical resonator, we are going to have two mirrors that can trap light inside it. And in our scheme, this mirror is going to be levitating under the action of repulsive Casimir forces. The reflectance of this kind of system has these features here, where we have this narrow minima whose wavelength is given by this expression here, where we have the refractive index in between the two mirrors, the cavity size, and then the order of diffraction, basically. So this is what we are going to do. We are going to characterize with spectroscopic techniques our system. From the reflectance, we are going to get information of the cavity size and therefore of the levitating distance. And then we are going to be able to tune the equilibrium distance by playing with the materials in between the two mirrors. And with this, we will tune this position. So we are looking for the following conditions. We want to have a repulsive Casimir force to have a stable equilibrium position. We want to have a sharp spectral features to accurately determine the equilibrium position. We want them to occur in the optical regime. We need to use well-known materials because we need the permittivity in an infinite frequency range. We need them to be experimentally feasible. We are going to work at the nano or macro scale, and we need them to be stable in time. And for this reason, for instance, we discarded alcohols because they evaporate very easily in time. So this is the scheme we attain. We have an upper mirror that is composed by a bilayer of polystyrene and gold immersed in glycerol over a substrate, which is made of a semi-infinite gold, and then on top a silica layer. And as you can observe in this graph, these materials fulfill the inequation I told you before. So for this set of parameters here, I show you the force as a function of the separation distance in logarithmic scale. And we can see that the force changes to be repulsive, to be attractive, and this is shown by this abrupt minima here, which corresponds to the equilibrium position of our system. In yellow, I have the Casimir Lifshitz force. In green, I'm incorporating the effect of the gravity and buoyancy. We also analyzed the effect of potential electrostatic forces occurring in our system, and for this we implemented the Poisson-Boltzmann methodology, and we considered what happens if we include a monovalent salt diluted in the glycerol, and we observed that for large enough concentrations of this salt, the response is basically the same, whereas if the salt, the amount of salt is not enough, then we will have an additional repulsive component. So from now on, we are going to consider just that we have included this amount of salt, and everything we are observing is really related to Casimir forces, gravity, and buoyancy. So we did our calculations, and then with these plots here, I am showing you that it is possible to tune the equilibrium distance as a function of the thickness of the polystyrene, the gold here, or the silica slab here, and we can tune it from some tens of nanometers to several hundreds of nanometers. If we consider this part here, and we have a look about the spectroscopic response of this system for silica layers of 100, 300, and 600 nanometers, we are going to have this kind of response. Another thing that we checked carefully is the fact that we need some certain high quality factor in our resonators, which is not really high. It's above 150, but still you need something like that to really discriminate between systems that are really levitating, which correspond to this gray curve here, and it is a thick curve, because we are taking into account a 5% error that could arise from some experimental sources, rugosity, misalignment, and stuff like that. And clearly, in this case, other systems out of equilibrium are being distinguished from the one that is really levitating. In contrast, if your design is not good enough, then systems in equilibrium or out of equilibrium are not being distinguished. You get the same response, optical response. So we fabricated our optical resonator. First, we fabricated, I'm going to be very fast because we didn't get the expected results. So we fabricated the polystyrene layer, then the gold film, different techniques, then the bilayer of polystyrene and gold, and checked the size of the systems we are considering. Then we also fabricated our substrates, first with a silicon wafer and then with gold, and these images show the optical quality of the materials that we are preparing. And then we also fabricated the whole system, the optical resonator, but without the glycerol in between. This is a SEM image of the system, and we could characterize it experimentally, and the fitting with the transfer matrix method was also fine, which means that we can really say what is the thickness of our materials, and therefore we should be able to get an information of the equilibrium position accurately. The thing is that when we included the glycerol, the upper mirror, the polystyrene and gold bilayer, started to roll up. And we tried, probably it has to do with some mechanical stress in between the interface of the two materials. We looked for different solutions, and I'm going to skip this because in the end we have to redesign the system, change the glycerol by water. Now we have an attractive force. Anyhow, the system should levitate. So we measured our system, we did the fitting, but we were one order of magnitude farther than our design told us, right? So when we were dealing with all this, then it happened. So by that time, the group of Xian Zhang in Berkeley demonstrated experimentally this idea. So basically, their system consists of a gold flake, which is much smaller. It's a micrometer square, and our ones were like this big, immersed in ethanol over a gold substrate with Teflon in their case. So they did the optical characterization, and from this they could extract the information of the levitating distance, and by changing the thickness of the Teflon, they could tune the equilibrium position. So similar idea, they succeeded, we just did the idea, had the idea. And now, very fast, because I think I don't have much time, I would like to show you very, very fast a different approach in which I want to show you that by changing the optical properties of your material, you can really tune the Casimir Lifshitz force. In this case, I'm going to consider a matrix of a material, and then I'm going to include inclusions of a different material. So the question was, can we tune this Casimir force by modifying the absorption properties of the composite material? Probably yes. If I change these bands, then I will change this, and then I will change the relation in between all my materials. What if we combine host and inclusion materials, which in bulk display Casimir forces of opposite nature? This is polystyrene, this is silica, and under similar conditions, they present forces of similar intensity but opposite sign. So if I combine them and change the amount of material, I will probably be able to to tune this force. Can I also trap it? Well, the difference in between an homogeneous film and an inhomogeneous film with inclusions is that in this case, we are going to have some light that is diffused, scattered by these inclusions. So in this kind of systems are usually described through effective medium approximations like Maxwell Garnett, Drew, de Brueggemann, and some others, but it has been demonstrated that the use of different effective models gives rise to different forces, different estimations of the force. So what we did was to implement a different approach in which we have a Monte Carlo approach combining mean theory and Fresnel coefficients, so that we are going to consider actually scattering mean theory and the resonances that occur because of the inclusions. This, we have used it in many, many works before. And just to be very fast, because I see Jean-Jacques coming here. So what we did basically, just very fast, is that this is a different approach in which we are considering the effect of having a real inclusion of a given size, whereas in the effective models, this is not considered. It's just some amount of material. So we changed the optical properties by changing the size of the sphere. We obtain the permittivity of these models, and then we could really tune the trapping or the force as you want to, you would like to see it, by changing the size from 20, 50, or 100 nanometers, whereas with the Maxwell-Garnett approximation, this is fixed. This is what you are going to attain. And with this, I would like just to finish here, and thank you for your attention. And of course, Hernan, Victoria, and the funding. Thanks.